All right, so this problem was designed to see what you understood about rotational motion. So you've got some sort of disk and it's rotating in the positive direction. And while the disk is spinning, there's some friction there, which exerts a torque. And so that will eventually cause the disk to come to a stop. And the first thing you're asked to do is to sketch on the graph what the angular velocity will look like. Okay, so the angular velocity starts off at omega naught, and because of friction, it's got to eventually reach zero. So you're going to have some sort of line which at t1 gets to zero. The angular velocity must be zero because it says sketch a graph that could represent the disk angular velocity from the time it's started until it comes to rest. So this needs to end at zero. Okay, so that's the angular velocity. All right, now the angular acceleration is the rate that the velocity is changing. It is the slope of this graph. This graph's slope is negative the entire way, so an angular acceleration graph should be negative. It doesn't matter where you have it on here. We don't care what value it is. We just want to know that it's constant and that it's negative. It's not changing. All right? And so that actually got you, I think, a total of 4 points for knowing that this curve started at omega naught and ended at zero. So having some sort of slope that was negative, you got a point. Okay? And for having a straight line, because torque exerts, friction is a constant force that'll have a constant acceleration, the slope is the same the whole way. So having a straight line here and not a curved line got you the second point. Over here, you got 2 points. First of all, you got both points if the graph of this, even if it was wrong, correctly showed the slope of this graph. Okay, so if you knew that the angular acceleration was the slope of this graph and you correctly plotted that, you get both points over here, even if this one was wrong. Okay, so the idea here is that the slope is negative and constant, so the angular acceleration is negative. Okay. All right, the second thing they asked you to do is to find the, let's see, part B, it asks you to derive an equation for the rotational inertia of the disk. Okay, so whoops, I'm crooked here. So if you understood that we're going to use Newton's law, so that is to say that the net torque equals I times alpha, you get a point. Okay, now how do we find alpha, because we're trying to find the moment of inertia I in terms of these things here. Okay? So we know the angular acceleration is the change, or omega final minus omega initial divided by the time. We know omega final is zero. So if you know that alpha equals negative omega initial over t, the time that it took to stop, then you're going to get a second point. And then if you can put these together, I equals the torque divided by alpha, which is the torque divided by omega naught over t. And you can write this as the torque times t over omega naught. And of course, this is t1 and this is t0 the way they have it. If you knew that, you get your third point. Okay? So there's an alternate solution. You can pause the video and look at it if you want. You can use impulse because the angular momentum is I times omega. And of course, the angular momentum only changes when there's a torque acting for some time. So you can work it out from that idea too. You can get all three of your points there. All right, so the third part of the question then says, what happens if halfway through the time it takes to stop, somebody drips some oil, which causes the torque to reduce because there's less friction. And so we are seeing, can you make a sketch of that? So up until half the time, your graph needs to look the same as your first graph. The angular velocity will decrease, but once you start dripping some oil on the axle, it doesn't decrease as fast. The slope starts to decrease as you add more oil. So the graph would look something like this. So we're looking to see whether there's a clear change in the slope at t equals 1/2 of the time. Again, the angular acceleration needs to be the slope of this graph. So from 0 to t over 2, t1 over 2, you need to have a negative angular acceleration. But then as you start to add oil, the slope gets closer and closer to zero, so the slope starts to increase, and it can increase in any way you wish here. You just need to show that the slope changes there to get all your points. Okay? So that was part C. So part D is a little trickier, and this was kind of the money points if anybody wanted to get a perfect score. If you're trying to mathematically model the magnitude T of the torque exerted by the disk, you need some equations. The question asks, which one of these equations is mathematically better? Okay, so you need to figure out which one of these equations produces a smaller torque as T gets bigger. So when T is greater than T1/2, so we're talking about, so here's the angular acceleration. The angular acceleration is negative, and then it gets less like that. So you can think about just one of these, which one is going to make the most sense, and the answer is the second equation is going to make the most sense. And why is it going to make the most sense? Because here, as time increases, the torque will actually, as T gets bigger and bigger and bigger, the torque actually increases. And here we know the torque must be decreasing because the angular velocity is getting closer to zero. So having a sense that 2 is a better equation because it behaves in the right way is the point there. And that's only worth 1 point. And no matter what the question's like, there's going to be some part of it that's really difficult, and you shouldn't get scared of that. Just work your way through. I think that the graphs on the first part were fairly straightforward, and you could have gotten most of your points there. So don't fret about this last part. It's kind of confusing.